Hey, what's going on, folks? It's Mike here, and welcome back to the Deep Programming Language series. In today's lesson, we're going to be taking a look at a new keyword that's just two letters, is. And you might have seen this in a few other programming languages, but I want to go ahead and talk about why it's an important keyword in the deep programming language. So with that said, let's go ahead and dive in on dlang.org in the documentation and the language reference. Now, where I'm going to go here is expressions. And let's just go ahead and minimize this for a moment, and I'll go ahead and scroll all the way almost to the bottom here to is expressions. Now, here's the actual grammar for how to use this, and you can see that this is a keyword here, is, two letters again, that can be used in multiple different scenarios. But I want to go ahead and just demonstrate the problem that this solves for us. So, for instance, let's go ahead and say that we're writing some code. Let's just go ahead and start with a simple if statement here. And I want to check if 5 is some sort of integer here. And let's just go ahead and compile it, and I'll say 5 is indeed an int. Something like that, and I'll go ahead and try to compile this program here, and I'm going to get this error here that says incompatible types for 5 equals int, cannot use equals with types here. So of course we want some way that we can go ahead and check if this works here. So let's go ahead and see if we've learned a few things here. So I could do type of, which we've looked at in this series, and again, if I check here, incompatible types for int equals int, cannot use equals with types. So again, we need some sort of keyword or some tool to actually evaluate this specifically for the types, not the actual values that are being stored here. So what I have here then is the is expression, which fixes that problem. Let's go ahead and fix that problem, and we'll see exactly what that is. So I'm going to say is, and then wrap this in parentheses because it is a expression. Try to compile it, and it will work here. If I actually run our program, 5 is indeed an integer here. So that's great. Now we have a tool here that's going to be really, really powerful for things like template constraints, checking types, if I have an alias, if I have some unknown type, to just see if it is this exact type or compatible with this type here. So let's go ahead and look at is expression. So an is expression is evaluated at compile time and is used to check if an expression is a valid type. So again, very important to see that this is something that's evaluated at compile time. So we could do some different tricks here, like for instance, put this in a static if. Let's go ahead and recompile that and rerun it, and it'll work just the same here. Or even better, let me comment this out here. And I'm going to grab this block here. Let's go ahead and just grab that block. Paste it because I want to reuse it, and I can put it in a static assert. So at compile time, I'll check this condition here, and I can do my same message here and say 5 is for some reason not an int. Okay, so that's the message that'll get printed out if for some reason this does not evaluate to true. So I can compile it, and again, no problems here with my program here. But if I change it to something like, let's go ahead and just break this code just so we can see how it functions, a float, and then I go ahead and at compile time, I will get that assert message that says 5 is for some reason not a, and then I need to, change my error message here. But the point is that 5 is an integer. It's not equivalent to a float, so then you'll get your error message printed out here. Okay, so that's the idea. Let's go ahead and make this a true condition because that's what we want to assert. And again, that's just an example of how you can use is expressions to evaluate at compile time. That's what the static assert does, or static if statement, that these types are equivalent in this case. So again, here's the use cases that we have with is statements. We can compare types for equivalence, again, to make sure that indeed 5 is an integer. We could also do other more powerful things like determine if one type can be implicitly converted to another. Okay, so what do we mean by this here? Let's go ahead and just do an example here. Let's go ahead and do, again, I'll do it with a static assert here. And what I want to go ahead and check is my expression here, 5, is that able to just be converted into a float here? And I'll say 5 is implicitly convertible to a float. Okay, so let's go ahead and test this out. If I compile it, oops, let's see, I gotta make sure I get all of my parentheses right. And again, this isn't for, I'm gonna make this mistake a bunch of times probably in this video, looking at 5 or a float. Again, that's what our type of is here, because we want to actually check if the type that 5 is, which is an integer, is perhaps convertible to a float here. Okay, so let's go ahead and make sure we save, compile, And indeed, I can treat an integer or convert it to a float. So for instance, if I have some function that takes in a floating point parameter, I can in fact convert it to an integer. And let's go ahead and just test that theory here just to see why this was useful. So I'm going to just create some function here. I'm going to say it takes in a float f. It's not going to really do anything, but I should be allowed to create some variable x here, call this function, pass in x, and that's not going to cause any problems here because I can do that implicit conversion. Now let's go ahead and try to flip this around here. Again, just playing around with these tools here. And let's just go ahead and say, can I convert a float into an int? And let's go ahead and say, can convert float to int. Well, we don't know. We're just doing this test here. Let's check at compile time. No, we can't do this. So for instance, let's go ahead and change this function around here. Let's call this function2. And this time I am going to, what should I do here? Let's see. We'll just reverse it here. Let's just take a integer here. And let's give ourselves a little bit of space here. That's what I want to show here. So let's try in this use case here where I have a float. I'll just call it x2. And for func2, can I pass in this float and have it implicitly converted, meaning without any sort of cast here? Will that work? Well, based on our assertion, right, this isn't going to work here, okay? So I want to go ahead and say that this is not allowed. So I'll go ahead and negate it. But we should still get a compiler error at this line here because, again, based off of our rule, we cannot, and let's make our error message line up here, cannot convert floats to integers here, okay? So here's our error here. It's not callable by passing in this floating point into this integer type here, okay? So I would have to do some explicit, right? So it can't be done implicitly, cast here to say that, yeah, actually just treat this as an int, you know, do the cast here. And again, D doesn't let you do the C style cast. So you have to write out cast. Again, we've talked about this in previous videos long ago, and that's because it becomes easy to find where you do these casts. And now that's allowed here, okay? But we can sort of understand how we can use is to figure out some of these type system things here, which I think is useful, again, just to use some of these programmer tools to remember some of these rules and do these little experiments. You can also do things like finding subtypes, for instance. So let's go ahead and just do a little example. And we really haven't talked about classes yet in this series, but I do still want to do an example because I think this will be familiar to you in other languages. But if I create class A here, and I create class B, which derives from A, let's go ahead and see if B is in fact a subtype of A here. Okay, so we'll do our static assert, and we'll say is, and I can't actually remember how to do this. I think I can just do B a subtype of A like this, and say B is a subtype of A. Let's go ahead and just try that out here, and that works. Let's go ahead and flip the order. Is A subtype of B here? And that doesn't work here. A is a subtype of B. No, because A is the parent class here. So again, you can use this is expression to see, again, if you have a derived type and can use it, you know, anywhere where you'd want some sort of polymorphism. Okay, so we haven't talked about classes in the D programming language, which are reference types and allow you to do these types of things, but you can see that this works here. Okay, let's go ahead and put a not operator here. And then you can also deduce the template arguments of a type template instance. Okay, I might have to look at the help for this one, but let's go ahead and just recap here what we've learned so far. So again, the result of a is expression is a Boolean, which is true if the condition is satisfied, or false if not. So we looked at several examples here. This is the predominant case, checking if these types are equivalent. So again, it's important to remember that is not the same thing as like equals equals or something. Like I'm not doing 5 equals equals 5, because we're looking at the actual types here, like int and then the type of 5, which is an int, and that works here. So that is the idea here. The other thing that I haven't talked about quite yet, the other thing that's useful for is to check that a type is semantically correct here. Okay, so if I have something like this, for instance, or something like this. These are just sort of seen as like nonsensical here. So meaning, right, I need to do is type of 5 here. I need the actual type here, right? This itself is just some sort of value. This is, you know, like an array of arrays. It doesn't really make sense here, right? So that's what this example is showing, that this is well formed. This type of this thing, which is an integer, is equivalent to the line above. Again, it's the same thing here. We can have, let's see, if I have something that's not defined, right, which is not well formed here, that works. Type of int, that's not an expression, right? We want like type of 5 or something. And then again, I can't just take the value here. And again, we have a function here, some function type here, so that's well formed, but an array of function or something, right? That fails here, right? This array of functions here, okay? Let's see. I showed the specialization example that was here with the classes, or sorry, when using this sort of type specialization, this is basically say if something's implicitly convertible, okay? So that's just something that you can keep in mind there. So again, I can convert this short, which is what the alias bar is for, to an int. That's fine, right? I could take a smaller type and pack it into a bigger one here. I can't do this. These aren't compatible in any way here. Bar can't be, you know, which is a short, converted to a string in any way without, you know, explicitly doing so and doing, you know, the bit by bit like conversion or something. Let's see what else we got here. We got the type specializations here as mentioned, which is just, again, checking if these types are equivalent. We've got a few other things here that are kind of interesting here, getting into the nitty gritty. And these have to do with, let's see, if the type specialization is a type constructor, let's go ahead and see what do we mean by type constructor? Okay, so const, immutable, in, out, or shared. Okay, so always good to kind of follow the documentation here. So const is const is const here. This is an int here. We follow within the parentheses, reading inside out, which is not const here. So head is indeed mutable here because again we could point this to other things here. And this is immutable, which is not const again. So we could see just pay attention to the exclamation marks here. We can look at different things like if an object is a class, module info is a struct. Again, int is not a type of class here. So again, some more powerful things here. So we kind of get the idea of, you know, hopefully these different rules here. I'm just kind of looking and see if there's anything interesting here. Where this starts to get interesting is following on our previous lesson where we talked about the idea of template constraints. This is known as concepts in other programming languages. So let me just give you an idea here of where we can use these as expressions. Like, let's say, for instance, I create a struct here, and I'm just going to call it, you know, my type. I'm going to parameterize it with t here. And let's go ahead and just have t and some value here. And let's add a template constraint, which again is just an if conditional here. What I want to do is say if t is an int, then this is okay. Okay. And let's evaluate that as an expression if t is an int. Okay. So this should compile no problem here. Now let's actually do an instantiation, which will be checked at compile time. So my type of int, you know, test here. Let's go ahead and see, does that work? That works fine. Let's go ahead and try a float here. Okay. And that is wrong, right? So this condition is not satisfied. We are only taking ints here, right? So we would need to do something like or is t equal a float. Okay, just looking for specific types here. Oops, and I gotta make sure that I save here. And I gotta rename these variables to something else here, test2. There we go. But this should be okay now, okay? And again, just to show that that previous example should be working here. Float, test2. So this wasn't working here, no good. But this, oops, let's forward in time here. And add our is expression, or is t equal float. Now we saw last video, if you watched that, we have different things like is number. We could write this out as some sort of like helper function that could be evaluated at compile time to return true or false if we had a bunch of these different types. And again, the traits library can be very useful. In fact, let me go ahead and just bring up the traits library really quickly in the library and search for traits. If you didn't catch that last video, these are the different types of things you could check, like, is it a function? Is it safe? But we're most interested in types, so we could say is, some common type here. In fact, let's go ahead and see if we can find is in parentheses, right? So here are some examples of saying is, and then we have in and out for the in type here. Again, so a few different examples that you could look at in the traits library to check like the constness or these types of things here, okay? So anyways, with that said here, let's go ahead and scroll down, see if there were any other useful cases here. That should cover most of the is expression here. Is expression. There we go. I think we got everything here. Yeah, we talked about classes we haven't really talked about, but again, those are different things that you can check here to say, you can even do these kind of interesting things here to see like for is foo here, for instance, some sort of function here, meaning like, does it return? Okay, so you can check if it's a function, a delegate, or a function pointer. So that's kind of neat here. I think that pretty much covers all the things here. Here's again the type specialization here. And this example I'd say is a little bit more wild because it has a this here, which we haven't talked about inside of our struct here, which is basically how we can treat this as a pointer or treat I as a pointer to this struct here. But you can see it's matching against that pointer. So our specializations can't have pointers here when we're checking things. So again, pretty powerful stuff here. Let's see what else we have. I think that's going to pretty much capture everything that I want to talk about here. Again, we have the parameter list forms here. Actually, this might be a little bit useful to make bigger here. Expression. Let's go to the bottom again, just to check the parameter list forms here. And this example is getting a little bit more wild here, but if we just kind of read here to get a little bit of help here, it's saying that we can basically do more complex pattern matching. It's still pretty clean in the D language overall, but if I have some alias here, for example, like this tuple2 here, so I've got my tuple type here, and then I've got this tuple2 thing here, which I say is an int and a string. Okay, so it's just a tuple with an int and a string. And I basically just want to check if the two things that are the same here, so this is using traits, this is the same exact line as above here. Let's focus on is, for instance, here. Is a template here that I pass again here with the given arguments that I'm checking against with int and string, the same as tuple2. Well, you can kind of again just pattern match that it is, right? There's the tuple with int and the string, which is exactly what tuple2 is. So that's sort of the basic idea here, okay? So again, a little bit more to think about. And again, this line above it using just traits for is same and comparing template with the tuple here is the same thing here, okay? Let's see, last things that we can do here is doing some matching against an associative array, which we're looking for the key and the value here for the type here. So that's the basic idea here. Okay, so with that said, that pretty much wraps up the is expression. So hope you enjoyed that lesson. Again, a lot of languages don't have is expressions, or at least if you're coming from like C++ or C, right, you're probably not used to seeing this. We're used to seeing like op equals and these sorts of things. So again, it's just important to keep in mind that this is for type checking. It's a little bit different than the equals operator, for instance. So again, we're just checking for types. And there's a nice example here. Like if I create floats f1 and f2, for instance, if I'm checking if f1 is equal to f2, let's do this with static asserts here. Static assert is f1 equal to f2. And let's go ahead and say f1 equal f2. That's the test that we're doing here. But if I'm asserting is f1 equal to f2, let's go ahead and put our little message here, is, for the expression here. Now this shouldn't compile. One of these is going to fail because, again, remember what we talked about here, meaning that is going to check the types here, and one's going to compare if the values, well, F1 and F2 are both instantiated to NaN, so they're actually going to not be equal here. But let's see. F1 cannot be read at compile time while evaluating. Let's see here. So it crashed at line 41. So it didn't like this here. And it's saying it can't be read at compile time. Okay, so let's go ahead and let's just make these asserts here so our code actually runs. And if we actually run it, we do get an assertion here. Doesn't like this. That's not true. Let's see if we were to comment this out. So this is false, not evaluated to true. Okay. Let's go ahead and compile this. Now, oh yeah, now this one I've got to use the few different ways I could do this here. I could let me write this right. Is F1 is F2. Let's go ahead and see. And let's just go ahead and put this evaluate here. Let me actually see if I can do this, just playing around with the language a little bit here. Let's see, let's wrap this up here. I don't know if that's actually going to work here. Oops. Yeah, that does compile here. Okay, so we could just test this as we think about these in the deprogramming language as sort of like identity. Like, is this a float or whatever here? So again, my assert here, right? This needs to be the type of, oops, F1. So we can evaluate this at compile time and get rid of that error message, a nasty error message. And let's see if this compiles and this runs here. This does evaluate to true if we do want to do these types of use cases of is at runtime here. Okay. So that's kind of nice here. I guess we've been doing things with the expressions here for evaluating every single time here, but that's okay. But this is just another use case for checking, like, is this, is the identity the same thing, the underlying type? Both of these are floats, so again, that evaluates at true here. Okay, so with that said, I think we've covered pretty much everything, including the distinguishment between equals now and is. So again, not exactly the same things, but pretty close. All right, folks, so with that said, hopefully you enjoyed this lesson. As always, check out the previous lessons here. Let's go ahead and find that deprogramming language series here if you want to track your progress on courses.msha.io. And as always, folks, look forward to your comments, discussion of is. If you have other ways to think about it or have seen it in other programming languages, I'd be kind of curious to see it with other languages especially, and see if they follow D rules or if there's any differentiators that might be important. So anyways, folks, with that said, we'll go ahead and close off this lesson. Thanks for your time and attention as always, and I'll look forward to seeing you in the next one.